Hi, I'm Melissa from Group 23. Our project is an automated plant care system with rotation, irrigation, and shading capabilities. As you can see on the next slide, our team members are Christina, Abby, and Brian, and myself, and we're all electrical engineering students. This project aims to give everyone the opportunity to garden. Gardening is a hobby that not only provides fresh food to its participants, but gives them the opportunity to be outside and get fresh air and sun. Not to mention, plants intake carbon and output oxygen, making them a huge boon to the environment. However, busy schedules and lack of gardening expertise can discourage many from pursuing this wonderful hobby. But with a self-care plant system, one does not have to worry about maintenance, but simply enjoy this plant's benefits. For this project, we needed to provide just the right amount of sunlight and water for the plant without the plant owner's intervention. Also, make sure the plant does not grow slanted, such as from leaning to the light source. Finally, we needed to provide an application that allows the plant owner to keep track of and make changes to the plant's maintenance schedule.
When it came to the physical design of our senior design project, a rough model consisting of all of the parts connecting and interacting with each other was constructed through the use of SolidWorks. As one can see on the top left of the slide, the bottom of the project consists of a water basin and a pump. Above that, as seen in the lower left-hand corner of the slide, is the compartment that will hold all of the electrical components, including the battery, PCB, temperature sensor, and one of the motors. Although in our 3D model, the representation for some of these parts is limited to a basic solid-colored cubic box, the dimensions are accurate to what will be used in the final product. This ensures everything will fit together nicely. In the middle of this slide, one can see the top of the electrical component enclosure and the turning table that will be used in order to rotate the plant so that it may obtain an even amount of sunlight on all sides. In the top middle photo, one can see a model of how the pot for the plant will sit on the turning table, as well as the water emitter, moisture sensor, and solar sensor. Finally, in the image on the bottom right-hand side, one can see the stand that supports the shading system and solar panel, which both attach to the side of the enclosure. In this final slide for the physical design section, one can see what the entire system will look like disassembled, and how each part will fit together. Overall, the system will be approximately 30 inches tall and have a base diameter of about 12 inches in order to accommodate a wide variety of plants and pot sizes.
A similar project was performed during the spring 2020 and summer 2020 semester called Easy Herb, which is a remote access hydroponic herb growing system. This design has similar implementations as our project, such as an irrigation system, light, temperature, and moisture sensor, a Wi-Fi module, and an app for remote access. However, this project aims to grow just herbs and is powered by a wall outlet. Also, it has other features such as a lighting system and nutrient pump, but it does not have a rotation or shading system. Even though it is a similar approach, the project aims to achieve different goals and requirements. This is the overall project block diagram. Here, the different subsystems of the design can be observed, along with the color coding based on the member that is primarily responsible in designing it.
For this project, the requirements and specifications have been broken up into 3 tables, each focusing on one section of the code. The power system is required to have an output power greater than 20 watts. This is to provide power to all of the sensors and systems while remaining power efficient. For the battery, the capacity must be greater than 5 amp hours in order to provide a sufficient power supply to all components. The solar charge controller must have an output voltage between 12.6 and 13.7 volts. Finally, the voltage regulators must have an output voltage tolerance of 4% to ensure accurate regulation of 3.3 and 5 volts. For the irrigation system, the system must have an operating voltage of less than 12 volts and a response time upon input of less than 10 seconds. This is to assure that the water can fill the pot when requested while remaining power efficient. The light sensor must detect values greater than 7,000 lux while displaying its measurements in less than 1 second. This is to assure it accurately measures the intensity of the sun. The moisture sensor must display its measurements in less than 1 second to ensure an efficient water detection for the irrigation system. Finally, the rotation system must complete a full rotation in less than 30 seconds. The Wi-Fi module must have a maximum current no greater than 250 milliamps and be capable of using the 802.11 protocol or the HTTP response 200. This is to create a power-efficient system while successfully communicating with the Arduino microcontroller. The microcontroller must have current less than 50 milliamps and an operating voltage of 5 volts. This assures that the microcontroller can sufficiently control the system while remaining power efficient. Finally, the app must be able to pull data from the database in less than 1 second, update the status page in less than 5 seconds, and access time in less than 3 seconds. This is to provide a more user-friendly experience with the quickest response time possible. Going over a few of the flowcharts concerning the software's operation, the first flowchart that is covered is the one for the irrigation system. The irrigation system will work by pulling the moisture sensor every 2 minutes, and will compare the moisture level to a preset level that is specific to the current plant being used. If the moisture level is below the established threshold, the system will signal the water pump to turn on, and the plant will be irrigated in order to reach an appropriate level for the plant. The next system that was mapped out with a flowchart was the shading system. This system will utilize the light sensors in order to determine how much sunlight the plant life is getting and shade the plant when the optimal value is reached. The way this is done is by pulling the light sensor every 2 minutes and accumulating the values of solar intensity. After the accumulation reaches a value that is deemed appropriate, the shading system will deploy and the plant will be shaded for the remaining fraction of the day. Also, on the right-hand side of the flowchart for the shading system, a demonstration of how the shading system may be used to protect the plant from overwatering due to rain is displayed. The shading system will pull the moisture sensor, and if it realizes that the value is far above a preset threshold, the system will determine that it is raining and deploy in order to protect the plant from being flooded. Finally, the last flowchart that was produced was that for the rotational system. This system works by changing a state variable depending on the plant's position and sends signals periodically to the motor that controls the turntable in order to ensure the plant receives an even distribution of sunlight on all sides. When it came to controlling the direction of the motors for this project, a motor control driver had to be purchased. When selecting this chip, we fell on the L298N, dual full bridge driver. This driver was selected because it's able to energize and control the 2 separate motors at once, as well as provide enough power to each of the bigger motors within the system. Initially, we implemented a pre-bought chip, but after consulting the datasheet, we understood that we could implement the control driver directly on our own PCB. We decided to implement the motor control chip on the breadboard in order to streamline the production process, save on parts, and minimize our overall production cost.
After researching light sensors, it came down to 2 options: a photocell or the SparkFun ambient light sensor. Photocells are produced by a wide variety of manufacturers and can be purchased through any of them for an average of $1 each. The device uses a photoresistor which produces an analog output which would be sent through the analog pins on the board. It can detect light up to 10,000 lux and operates at a voltage less than 100 volts. Finally, the device will be connected through a through-hole. The SparkFun ambient light sensor can be purchased for around $5. This sensor utilizes a photodiode which is attached to the surface-mounted quick port. It produces a digital output which will be sent using I2C protocol via SparkFun's Arduino library. We opted for the SparkFun sensor because of its wide lux range, quick port connector, and I2C protocol. The high lux capacity allows for direct sunlight, unlike the photocell, and the quick port makes it very easy to connect to the PCB and have the sensor be placed for best light detection. Finally, the I2C capability, coupled with the Arduino library, provides straightforward communication every time. The temperature sensor is responsible for detecting the temperature of the air surrounding the plant. The 2 candidates are the TE Connectivity NTC10K Thermostat 0603 and the SparkFun TMP102 Temperature Sensor. Both are products of SparkFun and are connected via surface mounting. The NTC uses a thermistor and produces an analog output, while the TMP102 uses a digital temperature sensor and produces a digital output. The NTC will transmit data through the analog pins, while the TMP-102 will send its data through the I2C protocol. The TMP-102 was chosen for its accuracy and I2C capability. Using this sensor over the NTC will allow for a more accurate system and more efficient code. The options for the moisture sensor, which will detect the soil's water content and activate the irrigation system, were the Keyees Soil Moisture Sensor and the SparkFun Soil Moisture Sensor. The Keyees version is less expensive, includes a comparator to produce analog and digital outputs, and runs at 3.3 to 5 volts, similar to SparkFun's. However, the SparkFun version has more documentation via SparkFun's website and has a higher quality with gold plating. Thus, the team felt the SparkFun version was a better fit.
The microcontroller is the brain of the project. It will be responsible for analyzing data from the sensors, comparing it with the inputs from the app, and sending signals to the various subsystems accordingly. The chosen microcontroller must house multiple GPIO pins so it can connect to all components within the project, must be compatible with the sensors, must be able to conduct I2C communication, the chosen form of communication for the sensors and Wi-Fi module, must have a high clock speed to be able to process all requests efficiently, must be small enough to fit on the PCB, and must be cost-effective so the entire project remains under budget. After researching, the selection came down to two devices, Texas Instruments MSP430 FR6989 and the Arduino Uno. Both devices feature 2 kilobytes of RAM, a clock rate of 16 MHz, and enough GPIO ports to support the entire project. While the price of the MSP430 is lower than that of the Uno operates at a more convenient voltage. It was ultimately decided that the Arduino Uno would be the best fit for the project. To start, the Uno features 2 kilobytes of RAM, which is enough space to support the entire project and operates at a clock rate of 16 MHz. It features 14 GPIO ports, allowing it to communicate with all components. The price of $23 is a little higher than some of the other prospects, however, it is acceptable as it allows the overall price to remain below the budget. Finally, this board was chosen for its manufacturer. Because of Arduino's open source policy, the board is compatible with just about every component on the market, and a wide variety of tutorials have been created relating them. The tutorials will prove to be useful when implementing the design.
While determining the appropriate methods of communication between the app and the microcontroller, two forms were considered, Wi-Fi and Bluetooth. Wi-Fi provides better user security and a much larger range than that of Bluetooth. It also can operate on two specific frequencies, 2.4 GHz and 5 GHz. Bluetooth has a lower range and less user security. However, it has lower power consumption than Wi-Fi. Ultimately, we decided to use the Wi-Fi module over Bluetooth because the Wi-Fi module allows the plant care system to be accessible worldwide. Based on the needs of the project and specifications listed above, Wi-Fi was the clear choice for the communication system. The Wi-Fi module will transmit and receive data about the plant system to our web application. Among the many Wi-Fi modules available, there are two strong options for our project, the ESP01 and the Node MCU. As seen on the next slide, both use the ESP8266 chip, but the Node MCU has more communication features such as SPI and I2C and more general-purpose I/O pins, while the ESP01 is half the Node MCU's size and cheaper. Ultimately, the Node MCU was the best fit because of its I2C capability and processing power, which will be beneficial in sensor data communication.
This design will be powered via solar panel. However, the voltage and current from the solar panel varies depending on the amount of sunlight it receives throughout the day. For this reason, a solar charge controller is needed to produce a constant current and constant voltage to charge the battery properly. The output voltage of the rechargeable battery will be then regulated at different voltage levels to power the microcontroller and different sensors and motors of the design. The selected solar panel was the Renogy 10-watt 12-volt solar panel. Even though both the Renogy and New Power solar panels share similar characteristics, the Renogy solar panel was selected because it is lighter, just weighs 1.2 pounds, and it has bypass diodes which minimize power drop caused by shade. These are important characteristics for the weight and operation of the overall system. Also, it is corrosion resistant, which is important for the outdoor implementation of this design. The solar charge controller design is based on the CN3795 integrated circuit from Consonance Electronics. Even though both the CN3795 and CN3722 share similar characteristics, the CN3795 provides a wider input voltage from 6.6 volts up to 30 volts. Also, this controller works for single and multi-cell lithium-ion, lithium iron phosphate, and lithium cyanide batteries, and it can automatically recharge the battery when it falls below certain voltage when connected to a solar panel. This solar charge controller provides a constant current and constant voltage charging mode, and its charging current can be adjusted by a current sense resistor, which is an important characteristic to charge the selected battery. The selected rechargeable battery for this project was the Extra Power 12 volts 5 amp-hour lithium iron phosphate battery. This battery provides up to 7,000 cycles and a complete protection with its unique built-in battery management system, which protects it from overcharge, deep discharge, overloading, overheating, and short circuit. It is portable with its dimension being around 3.5 by 2.8 by 4 inches and a weight of just 1.7 pounds. The lithium iron phosphate battery type was selected due to safety concerns since it has excellent thermal and chemical stability and it stays cool in higher temperatures. The project design requires different voltage levels to be regulated in order to provide the correct voltage to each subsystem. This is why the power system will have two regulating circuits with output voltages of 3.3 volts and 5 volts. The selected voltage regulator integrated circuit was the LM2576 adjustable switching regulator from Texas Instruments to be able to produce different output voltages by just changing some resistances. This IC provides an efficiency around 80 to 85%, which is considered good for our design. It is capable of driving 3 amp load with excellent line and load regulation. We also selected since we have experience working with them and designing them from previous courses.
An application was designed to go along with the project. It is web-based, meaning that it can be accessed by any device with internet capabilities. The app was designed in Adobe XD and then developed in Dreamweaver. It was uploaded to a server using 000 web host and uses a MySQL database. The app will have several capabilities. For one, the user will be able to select a new plant. They can do so by selecting the water and sun care routines from drop-down lists and submitting them to the microcontroller, which will be used for the plant's care. The user will also have manual control over the shading, rotation, and irrigation systems. Finally, the user will be able to view live updates of their plant on the plant status page. The data will be updated every couple of seconds.
Here is the entire PCB schematic. Our PCB consists of the microcontroller, sensor ports and pin header, voltage regulators, motor driver, Wi-Fi module, solar power controller, and relay, all of which will be shown in more detail in the upcoming slides. The chip shown here is the ATmega32A, which is used in the Arduino Uno. Most supporting components on this sheet are connected to it. The crystal, resistor, and capacitors provide it with the 16 MHz clock. Next, the sensor ports and connectors are shown. As said earlier, the sensors will be attached to the ports. The 8-pin header is provided for input voltage connections and troubleshooting. The three LM2576 voltage regulators are shown here. Step down the 12-volt rail to 3 volts, 5 volts, and 7 volts. The motor driver controls the motors for the rotation system and irrigation system, and takes input from the Arduino on when to put the motors in forward or reverse. Here is the Wi-Fi module. To the left is the ESP12F module with its programming circuitry and pin headers. And to the right is the reset, flash, and ADC circuitry. It is connected to the SDA and SCL pins or the I2C rail in order to communicate with Arduino and the sensors attached to the I2C rail as well. Next is the solar power controller with the CN3795 chip, which will charge the 12-volt battery using the energy from the solar panel, and its circuit includes overcharge protections. The 5-volt relay circuit turns on and off the irrigation system via a digital signal from Arduino. Finally, The final PCB layout from EasyEDA is shown in 2D and 3D formats, right here.
For economic constraints, the project is self-sponsored, meaning we have a limited budget and we have a time constraint of 2 semesters. For the environmental constraints, the solar chargers can only work when the sun is out, and because the project can be used outside, it must be designed to withstand high temperatures and heavy rain. For manufacturability constraints, all mechanical aspects and electrical equipment and components will be constrained to those readily available on the market. To assure an efficient process, all aspects of the design are constrained to things the group has experience with. For sustainability constraints, the project must be designed to withstand drastic climate changes, including the possibility of corrosion from rain and high and low temperatures, which could cause a variation in the operational levels of the circuitry. Therefore, the electrical components must be stored appropriately. For health and safety constraints, the group must always keep in mind water safety, the potential for injury during rotation, the materials used, potential fire, and potential shock. For social constraints, the project must remain affordable and small in size while maintaining an easy-to-use design. For ethical constraints, the group strive to maintain academic integrity and product honesty throughout the entire duration of the project. There were no political constraints found with this project.
When it came to the completion of this project, our group had to use the appropriate standards for some aspects. There were several battery standards that were in mind when completing this project, as well as quite a few standards for the solar panel. Also, when it came to the coding of this project, there were several standards that applied to the programming languages used, and the integrated Wi-Fi system.
The workload has been divided into 4 equal parts and assigned based on each member's strengths and interests. Brian will be primarily responsible for the electromechanical output systems, Abby is responsible for the application and software development, Christina is responsible for the power systems and electromechanical input systems, and Melissa is responsible for the sensors, modules, and control. Each member is also assigned a secondary task to assure that the project is completed in a timely manner. As shown in the pie chart on the right, the team feels that the workload has been distributed equally among all members.
The budget of this project is around $406 based on the acquired components to complete the overall design. This is below our established budget of $2,000. This gives us the opportunity to buy extra components for each system in case they get damaged during the assembly and testing of the overall design.
Overall, all the major systems of this project have been tested, including the motors, water pump, microcontroller, light sensor, moisture sensor, temperature sensor, Wi-Fi module, irrigation system, rotational system, and shading system.
All testing and implementation has been completed and the project is now fully operational. However, the group feels as though our project is not totally complete. There is still more room for improvement when it comes to software testing and overall design. For the time being, however, this design is sufficient for the requirements of the project.
Finally, although the project is done, there are many future improvements that could be made. Although we have the code working, we could program specific settings for specific common plans. Also, there could be many improvements to the physical design. Using better materials and 3D printing materials would likely save us on cost, weight, and also therefore power. Although we are happy with the output of this project so far, there are many areas that could be improved. Thank you for watching.